In this video, we're looking at rational functions. Rational functions are defined as a fraction where each numerator and denominator is a polynomial function. And we would like to include that our denominator cannot ever equal 0, just so we have that part covered. Now, if you take two polynomial functions and add them together, or subtract them, or multiply them, basically you get another polynomial function. But when you divide polynomials, we get a new kind of function called the rational function. And we can still think of, when we see that word rational, the word ratio is there, indicating that we're dealing with a fraction. Let's look at some graphs of rational functions. Here's a basic rational function, f of x equals 1 over x. Now remember that our definition of a polynomial said that a constant does count as a polynomial. So if you're looking at this 1 over x and wondering where our polynomials are, well, it counts even if our numerator is just a number. But we'll definitely see a variable in the denominator in that case. So 1 over x, a basic rational function, looking nice. Here's 1 over x squared, similar looking. 1 over x cubed. And if we take a quick look back at 1 over x, we can see that these functions do have some similarities. So the rational functions in some ways are like polynomial functions, where if we have an odd degree, we can see some similarities between those graphs, but other terms tend to cloud the picture, just like they would with polynomial functions. Let's look at 1 over x to the fourth. There's our 1 over x to the fourth, and it looks pretty similar to the 1 over x squared. They both have an even degree. There are certain characteristics of the graphs of these rational functions that we want to explore further. We want to see that this particular graph, the ends level off right at the x-axis, and towards the y-axis they both shoot upward and run right along that y-axis. And if we zoom out a bit, we'll see them just running closer and closer to that y-axis. We're never going to see those two lines cross. And in fact, think about this function 1 over x to the fourth. What is the value of this function when x equals 0? Well, 1 over 0 to the fourth would be 1 over 0, and that's undefined. So our graph actually will not be defined at x equals 0. It will not have a point when the x-coordinate is 0. It's never going to cross the y-axis. So we want to understand that these graphs can run alongside these guidelines. In this case, it runs horizontally along the x-axis. It runs vertically along the y-axis. It is actually not crossing either of these axes at all. It's not crossing the x-axis because that would mean our y value equals 0. And what value of x could we put into this fraction to make it equal to 0? Well, as long as the numerator is 1, this fraction is never going to equal 0. So because it cannot ever equal 0, we have no graph that is even touching the x-axis, and none of it is touching the y-axis either. Graphs like these arise once we start dealing with fractions, and especially because of this idea that the denominator cannot ever equal 0. So our graph at some places, it just cannot exist there, and that causes the graph to do some interesting things and make some of these moves where it runs upward forever or levels off somewhere horizontally. Let's look at some more examples. This function x plus 1 over x squared plus 4x plus 4, again we see it leveling off. Now in this case it does cross the x-axis. We actually do have values that can equal 0, but we still see a leveling off on the x-axis. This time we are able to cross the y-axis. We can have an x value equal to 0. It's not going to make us have a 0 in the denominator, but this time it looks like we are trying to avoid negative 2 in this graph. So there's something about this function that says 0 is okay, but negative 2 is not allowed. And I can even draw in a vertical line at negative 2. This line is x equals negative 2. And we're highlighting this line that the graph does not cross, but just runs alongside. And we'll zoom out and see that these two branches never cross. They run closer and closer to the line x equals negative 2. This line is called the vertical asymptote. In general, asymptotes are guidelines on graphs. Sometimes they can be crossed, other times it cannot cross an asymptote. Well, when it's a vertical asymptote, that is a kind that will never be crossed because that line is happening right at the value that would make our denominator equal to 0. If x equaled -2, -2 squared, that's positive 4. This middle term, 4 times -2, would be -8. So 4 plus -8 plus 4 equals 0. X value of -2 is causing us to have a 0 in the denominator, and that's not allowed. So we see a vertical asymptote at x equals -2. We will always see one of these vertical asymptotes at a value that would make our denominator equal 0. Well, there is one case that we'll see at the end of the video to clarify, but what I can tell you is that we will always focus on the denominator for what values of x would make it equal to 0, and we should understand that those points are not going to be on the graph. We'll often see our graph run alongside an asymptote, and that asymptote is a vertical line right at the value that would make the denominator equal 0. Let's look at some more examples. Here's x squared plus 5x plus 4 over x squared minus 5x plus 4. And this is an interesting looking graph. It looks like, well, it's hard to really tell. Let's zoom out a little bit. Interesting. So we see some leveling off on the ends again. The graph is really broken up into 3 separate pieces this time. It looks like it's running upward with these branches, but now we have another loop going on down here. So what's the reason for all of this? Well, we talked about the graph avoiding those x values that would make the denominator equal 0. And if you're quick with factoring, you might see this denominator we could factor as x minus 4 times x minus 1. And if we solve that, setting it equal to 0 and solve, we'll get solutions of 1 and 4. So we're seeing these vertical asymptotes at positive 1 and positive 4. And our graph is never crossing these asymptotes. And the fact that there are 2 asymptotes, 2 x values that the graph avoids, means that we have some extra pieces. We'll have a piece on the left of this left asymptote, and a piece of the graph that is in between the asymptotes, and another piece of the graph that is to the right of the asymptote on the right. Let's talk about where we begin to see it leveling off horizontally, because it's not at the x-axis, it's actually at the line y equals 1. Horizontal line, so it's a y equals. We'll plop in y equals 1 and see the graph does run alongside each of those. And in a bit we'll look algebraically at how we know exactly what the asymptote is horizontally. We're going pretty well with this idea that when the denominator equals 0, that's where we're going to see these vertical asymptotes. They're x values that are not allowed. The graph is never crossing those vertical asymptotes. Let's look quickly at a few more examples, and we'll point out some interesting things, but then we'll get back to the algebra side and show where we come up with the vertical asymptotes and the horizontal asymptotes and the rest of the things that we're about to see. So another example, 3x plus 2 over x minus 2. Still a rational function. We don't need these polynomials in the fraction to be very complicated. They don't even need to be quadratic. We saw an example, the first few examples, our numerator was just the number 1, and we had like x or x squared in the denominator, so we can keep things simple and still come up with rational functions. We see a vertical asymptote here, and checking out that denominator, hopefully we're seeing that at 2, this denominator would equal 0. That means we'll have a vertical asymptote on this line x equals 2. In terms of the leveling off, it's at the line y equals 3. We're seeing the leveling off on left side, right side. Here's an interesting looking graph. X cubed plus 7x minus 6 over x minus 2. It almost even looks like some kind of polynomial graph, possibly. It is continuous in terms of what we can see, whereas the rational functions we've looked at so far, those graphs have not been continuous. We've seen some separate pieces. So this one looks kind of interesting so far, but a good example of don't always believe exactly what you see when you first graph it. If we zoom out a little bit, we see that it is discontinuous. We have this branch that it turns out actually runs along a vertical asymptote and then picks up again up at the top. Very cool. So we do have our asymptote at x equals 2. Even if we zoom back in, we'll see our graph is not actually ever crossing that line at x equals 2. It's running just alongside of it. So it straightens out pretty well, and it's never crossing x equals 2. And at the top branch, this piece up here, we have a part that is also running along the asymptote at x equals 2. So one branch is running along the left side, and the other branch is running along the right side. But neither of those is actually crossing the line. Neither is crossing the asymptote at x equals 2. And we see this branch then shoots up skyward over here. Here's x squared plus 4x minus 7 over x plus 3. Vertical asymptote, we could spot if x equals negative 3, our denominator equals 0. So vertical asymptote at negative 3 looks good. We have each branch is running alongside that vertical asymptote. Horizontal asymptote, it's hard to see right now if they're going to level off or just continue out in that direction to the upper right and bottom left. Let's zoom out a little bit. And they don't level off, but they do tend to follow this straight line. So is there another asymptote here? There is a diagonal asymptote or an oblique asymptote. It's a line that is serving as a guideline for our graph. And that's another one of the asymptotes that can never be crossed. So vertical asymptotes will never be crossed. These diagonal asymptotes also will never be crossed, but the horizontal ones, they can be crossed. Let's drop in this line. I would do some algebra to find that the equation of the line, the diagonal or the oblique asymptote, is y equals x plus 1, and we do see our graph running right alongside of it. This is a similar looking graph. All I've done is change one sign. This is x squared plus 4x plus 7 over x plus 3. The one we just had an x squared plus 4x minus 7, the one in maroon. Interesting, and it looks like they both even have the same asymptotes, the same vertical asymptote, the same oblique asymptote. And that's kind of an interesting looking picture. Just a couple more. Here's 3x squared plus 8x plus 4 over x squared minus 4. And this graph might look very familiar. We've actually seen this exact graph before, back when we called it 3x plus 2 over x minus 2. The same graph. So we need to talk about how two rational functions can produce the same graph, and also, are those two graphs really the same? It looks like they are, but we'll see that there's actually a small difference between the two. And lastly, x squared minus 7x plus 12 over x minus 4. Near the origin here, it looks like the graph of a straight line, and if we zoom out, we'll even see that it is actually a line. At no point way out to the left or right is this graph doing anything really beyond just being a straight line. So we'll have to figure out what's going on to cause this rational function to produce a graph that is a straight line. And also with this one, do we truly have a straight line, or is there some other detail about this graph that we need to know about? Before we begin to break things down algebraically, let's talk a little bit more about those vertical asymptotes and some symbolism that we want to start to use. We describe vertical asymptotes this way by saying that our function, this arrow, means approaches, as in our value gets closer and closer and closer. Now, infinity is not really a number, it's just a way of saying forever in the positive direction, and this negative infinity as forever in the negative direction. So as our function goes further and further and further in the positive direction, this happens when our x values get closer and closer to some value a. A is just a number, so where we saw an asymptote at x equals 2, we could say that a in that case was 2. This negative sign up here is saying that we're coming from the left side, from the negative side of a on the x-axis. Now we're going to take these ideas to some graphs pretty soon to break them down, but let me just run through these. So this one is saying our y values shoot upward, get extremely positive as our x values get closer and closer to some number from the left side. Or, and it's if any of these four things happen, but we'll see that they do kind of come at least in pairs. The other one, our y values, the function values, get skyward, more and more positive as our x values get close to some number a from the right side, from the positive side. So these first two are examples of when the graph shoots upward when we get close to some number. And these two examples are for when our graph shoots downward towards negative infinity at some number a, and it can happen from the left side or the right side. So let's pull off some graphs to identify each of these situations. Here's a graph I like. F of x equals 1 over x, that first example we looked at. Now where we see our vertical asymptote is right at x equals 0, so our value of a is 0. And what we can say about what's occurring down here is that our function is approaching negative infinity because it's going downward, and this happens as we approach 0 from the left side. So we'll have a negative to say it's coming from the negative side. And up here, where it's also running along the vertical asymptote, this branch, since it's going in the positive y direction, our function is approaching positive infinity as x approaches 0 from the right side, from the positive side. Here's another example we had. X squared plus 5x plus 4 over x squared minus 5x plus 4. We have two asymptotes. I have them drawn there in red. So let's talk about what's happening as our graph runs alongside the vertical asymptotes. This branch here, it's going in the positive direction. Our function approaches positive infinity as x approaches, now what number is it in this case? Positive 1. So as x approaches 1, and our graph is on the left side of that asymptote, as x approaches 1 from the negative side, from the left side. We've got a piece down here. Let's deal with this one next. It's going downward. It's running down along that asymptote. F of x approaches negative infinity. As x approaches, it's still on that asymptote at 1. This is on the positive, on the right side of the asymptote. Down here, another one running downward towards the negative infinity. And this one is as x approaches what number? This asymptote at positive 4. And we are on the left side of that asymptote, the negative side. And lastly, up here, we're running upward towards positive infinity. F of x approaches infinity as x approaches which number? It's 4. And we're on the right side, the positive side. So those are a couple examples of how these situations play out. And remember that a is the number where our vertical asymptote is. We can say the asymptote is the line x equals a, and this applies to those vertical asymptotes. Now let's talk about those horizontal asymptotes where we saw our graph leveling off horizontally on the far left or the far right. What I want you to think about when it comes to horizontal asymptotes is because we see this going on at the far right of the graph or the far left of the graph, we can think about when x is approaching negative infinity, when our x values are getting smaller and smaller and smaller on the left side, and what happens when x approaches positive infinity, when our x values are large, 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 very large. And now the horizontal asymptote, we saw both ends leveling off on the same horizontal asymptote. So we really don't even have to think of both of these cases. We're really just interested in what happens when the absolute value of x gets very large, or when we get far and far away from 0, far from the origin. So we'll think about when our x values get very, very large, what is happening to the functions that we're working with. Let's go right to some of our graphs to break this down. This is always a good example to come back to. F of x equals 1 over x. In this case, our horizontal asymptote is right on the x-axis. It's horizontal, so it's a y equals equation. Y equals 0. We're not going vertically up or down at all. We're staying right on the x-axis. But our idea is, if we take this function and it's 1 over x, think about what's going to happen as this value in the denominator gets larger and larger and larger. So let's think about if we had 1,000 in there. It's a pretty tiny number. But what if x got even larger and larger and larger? Basically, our function is getting smaller and smaller and smaller. So it's getting closer and closer to 0. We could say that as our x values approach infinity, the function gets closer and closer to 0. So I'm looking at my function, and I'm imagining where I have my variable x, that it's a number that is large, extremely large. And then I think about, well, what is a fraction where the numerator is 1, but the denominator is a huge number? It's a very small, small thing when we have a fraction like that. It's basically getting closer and closer to 0, and that tells us where our horizontal asymptote is at y equals 0. Let's look at a few more examples. This one was another example where we have it leveling off on the x-axis, which is the line y equals 0. This function, x plus 1 over x squared plus 4x plus 4. Now you might start to look at all of these x's and think about, do I have to try to figure out what's going on if each of these x's is a number that's very, very large? That would become a little bit complicated, but there's an idea that we're going to use in these cases. Think about what happens if we have this function, x plus 1 over x squared. Now here I do want you to imagine if our x is replaced by a very large number. So let's start with if x equals 100. This would be a 101 in the numerator, and 100 squared, that's 10,000. So it's already starting to shape up like a pretty small fraction. What if we had x equals 1 million? 1 million plus 1, okay, and 1 million squared, that is becoming a pretty large number. We need more. There's 1 million squared. It's 1 trillion. 1 million times 1 million, 1 trillion. What we begin to see is that the denominator, where we have the x squared, that turns into a huge number much more quickly than our numerator does. Now granted, they're both getting pretty large, but where we have the higher degree, that's where we see it grow faster. So we actually can even ignore the x and just pretend like it is another number and think just about what happens if our denominator gets larger and larger and larger. Again, we get closer to 0. As x approaches infinity, this function is going to approach 0. And we're thinking that the x squared, it moves much more quickly. So we ignore that x and think about, well, if our denominator gets huge, that's a fraction that's going to get closer and closer to 0. So up here, we're taking that same approach. We're only looking at this x squared. It's got the highest degree. So what's a fraction doing if we have a numerator that's just a number and our denominator has x, or x squared? Well, as that x gets closer and closer to infinity, this is a fraction 1 over a huge number, gets closer and closer to 0. So we see our asymptote again at y equals 0. Let's look at another example. Now we're back to x squared plus 5x plus 4 over x squared minus 5x plus 4. We have a horizontal asymptote. The left branch, the right branch are both leveling off horizontally, this time not on the x-axis, but at the line y equals 1. So let's talk about what we see in the function that would show us that it levels off at y equals 1. So here's our function, x squared plus 5x plus 4 over x squared minus 5x plus 4. We know that we only have to focus on where we have the highest degree. But in this example, we have an x squared in the numerator and x squared in the denominator. Remember, the rest of these, they basically are so small compared to the terms that have the highest exponent that we ignore them. We ignore them when we're talking about x values that are very, 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 very large. So x squared basically is overpowering all these other terms that have regular x or just a number. So what about a fraction, x squared over x squared? Well, whether I think of x as 100 or 1,000 or 1,000,000, I'm always going to end up with the same numerator and denominator, a fraction that equals 1. And that's why we see our asymptote at y equals 1. We're thinking about x values that are getting very, very large. That means we can ignore anything that is not the highest exponent. We're ignoring all these terms aside from the ones that have exponent 2. And thinking of a fraction where same numerator and denominator, it's going to equal 1. Now this example has horizontal asymptote at y equals 3. What about our function is going to tell us that we'll have a vertical asymptote at positive 3? The function 3x plus 2 over x minus 2. We're thinking about x values very large, so we ignore any term that is not a high degree. In this case, the highest exponent we see is 1, so we can ignore the constants, but we have to deal with a 3x in the numerator with an x in the denominator. 3x over x, well, if we simplify that, we're looking at 3. There's our horizontal asymptote at y equals 3. Now our last example for talking about horizontal asymptotes is one where we had an oblique asymptote. An oblique asymptote, but no vertical asymptote. So what would the function show us if we take the same approach of thinking of when our x values are very, very large? We ignore the low degree term, so I see my highest exponent is x squared. So I'm losing the first degree x's, I'm losing the constants, and I'm thinking about what if this x became very, very large, and all I have is a, if everything cancels from the denominator, of course we're thinking it's like an x squared over 1, or just x squared. What happens when this value becomes very, very large? Well, it grows, it's squared. So if x was 100, this would become 10,000. What we're basically saying is, as your x values get very, very large, so do the y values. It's not leveling off anywhere. The further we go to the right, the more it's going upward in this case. And the further we go to the left, the more down it's going. It's not leveling off at all. And so when we look at our function and think about x values growing very large, if we come up with some situation where we have some term in the numerator but nothing in the denominator, that's an example of a function that is going to be increasing or decreasing on the ends. It's not going to level off at all. So we would have no horizontal asymptote. So a summary of the horizontal asymptote. Well, it's a horizontal line, so it's a y equals line, and I would always just want to think about this idea that we discussed, or I discussed at U, where we think about x values that are growing very, very large, and we look at our function and determine, is this something that is approaching 0, or it's approaching some number, or it's getting very, very large, so it's not leveling off at all. But some people also like to see the rules for these situations, so let's jot those down too. The first situation that we saw was if the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at y equals 0. Our examples were 1 over x and x plus 1 over x squared plus 4x plus 4. Examples where the degree of the denominator was larger. So if we thought about x values getting larger and larger and larger, we had some fraction that was basically a 1 over a huge number. 1 over, almost we could say it's approaching like 1 over infinity, and a fraction where it's 1 over a huge number, it approaches 0. So our horizontal asymptote at y equals 0. The next cases we looked at were rational functions where the degree of the numerator and degree of denominator were equal. We had x squared plus 5x plus 4 over x squared minus 5x plus 4. We had 3x plus 2 over x minus 2. Let's look at that one. That's a nice, tidy little example, 3x plus 2 over x minus 2. We thought about x values getting extremely large, so we ignored the constants and saw a fraction 3x over x. That x in the denominator is a 1x, so 3x over 1x. That's why we're looking at those leading coefficients. That as our x's get very, very large, they're basically going to cancel each other out. We only have to look at the coefficients to think about what number it is once it's simplified. So that's the example that had the horizontal asymptote at y equals 3. Our leading coefficients were in the numerator 3 and in the denominator 1. And the last case, I chose to squeeze it down here at the bottom. If the degree of the numerator is greater than the degree of the denominator, so those are basically the only three situations we could have. The first one, the degree of the numerator is less than degree of denominator. The middle case, if the degrees are equal. And lastly, if the degree of the numerator is the larger one, we'd have no horizontal asymptote in that case. We saw an example where we have an oblique asymptote or a diagonal asymptote, but in terms of horizontal asymptotes, we want to say, in this case where the numerator has a higher degree, there will be no horizontal asymptote. So let's transition over to the oblique asymptotes now, where we had the diagonal lines that our graph was running along. This function was our first example that had an oblique asymptote, x squared plus 4x minus 7 over x plus 3. Now in terms of what we've talked about so far, we just want to reiterate that we have this vertical asymptote where our denominator would equal 0. So I can set this denominator equal to 0 and solve and see x equals negative 3. Vertical asymptote at negative 3. We know it's not going to have a horizontal asymptote. It's not going to level off on the far left or far right, because for x values that are very, very large, our numerator is going to get exceedingly large. So the graph is going to keep increasing vertically, either upward or downward. The way that we know that we have an oblique asymptote is, for one, that our numerator does have a higher degree, but also specifically, it can only have a degree that is higher by 1. The denominator has a degree 1, the numerator has a degree 2. So we will have an oblique asymptote. If our numerator was x to the third, we wouldn't see this oblique asymptote. We'll see it here, where our difference of exponents, difference of highest exponents, is only 1. And the way that we'll find the oblique asymptote, in this case, we did know that it was y equals x plus 1. Here's how we'll find it, by division. We can do it with a long division. We can't even do it with a synthetic division. Let's do both. First, the long division. Now, I'm starting with the x times what equals x squared, putting the answer up top, keeping all my terms organized by degree. So my first degree terms right here in this column, multiply back down. That's the first time I care about that positive 3. It's a subtract here, but I'll often just flip my signs and add. Bringing down this, minus 7. And then next round, x times what equals that x plus 1. Let's multiply back down. And we have a remainder. So up here, that's where we're seeing the equation for our oblique asymptote. Y equals the quotient, x plus 1. There's the equation for the oblique asymptote. We did it with a long division. With synthetic division, let's see if we can squeeze it right up here. We know that instead of using the factor x plus 3, we would use the 0, negative 3. We're using our coefficients 1x squared plus 4x minus 7. Synthetic division, so we're bringing that one down, multiply back up, add down, multiply up, add down. Different remainder is a bad sign, because back here I didn't flip my signs and add. I should always do that. Negative 10. Okay, flip signs and add instead of subtract, because that's what keeps me accurate. So negative 10 ought to be that remainder. I'm feeling better about that. But here, our quotient, we know that these numbers are coefficients of the quotient. It's the constant 1. That's a 1x plus 1. So again, that's the x plus 1. Okay, our equation. Let's go to another example. Do we have another one where we can find an oblique asymptote? Let's see. Well, here's a brand new function that we haven't looked at yet today. Made it up just so that we could find the oblique asymptote. Function is 2x squared plus 9 over x plus 3. I know it will not have a horizontal asymptote because the degree of the numerator is larger. So as x gets larger and larger, so does the value of our function. It shoots upward in the positive x direction, shoots downward as we go to the left, negative x direction. We can find an oblique asymptote if we divide, because we also know that the difference of our degree is just 1. Let's do the division. X plus 3 divided by 2x squared plus 9. I need a placeholder, so I'll go with the plus 0x and the plus 9. Okay, division. So x times what is 2x squared? We need a 2x this time. Multiply back down. Definitely going to flip my signs and add. Let's bring down the plus 9. And now we need negative 6. Really don't care about the remainder at this point. I'm just looking for oblique asymptote. But it is 27, I'm pretty sure. Y equals 2x minus 6. So we're going to check it out and see if that's actually our equation for the oblique asymptote. Let's do a quick synthetic division, why not? Divided by negative 3 with coefficients 2, 0, 9. This is how I check to make sure I did the long division right. Let's multiply up, add down. Multiply up, add down. Okay, I did it better that time. And we know those are coefficients of the quotient 2x minus 6. So it looks like both ways I'm coming up with 2x minus 6. That's good. Let's clear this stuff out and draw in the line y equals 2x minus 6 and see if we're accurate. So that looks good to me. There's our oblique asymptote, y equals 2x minus 6. Now we have two more examples to look at, just to remind you what they were. We looked at this function, 3x squared plus 8x plus 4 over x squared minus 4, and pointed out that it was the same graph as 3x plus 2 over x minus 2. So we need to figure out algebraically why this is happening. Here are those two functions that produced the same looking graph. In order to show why they came up with similar looking graphs, we'll take our more complicated looking function and try to simplify it. Can we factor numerator or factor denominator or both, and then will we see some common factors that we can divide out? In the numerator, I've got a leading coefficient 3, so I'm doing this AC method. I'll multiply first and third and get 12. I'll see that if I can swap out this middle term and replace it with two terms that have a product also 12 and add up to 8x, I'll be able to factor by grouping. 3x squared, so 6 and 2 are those terms that I like. And then we'll do the factor by grouping. 3x with x plus 2. Here's a GCF of 2 with x plus 2. So we can factor this numerator and come up with 3x plus 2 times x plus 2. Denominator, hopefully we're seeing that one pretty quickly, a difference of squares, x plus 2 times x minus 2. Close that guy up. And there are those common factors, x plus 2. So a little bit of factor and cancel just to simplify our fraction. That's how we're seeing that it does give us the same graph as 3x plus 2 over x minus 2. But it's actually not exactly the same. There's a little detail, I alluded to it earlier, there's a little detail that we need to know about. So first of all, definitely we can say that you can simplify the fraction, and what you're left with, it's going to give you the same kind of graph. But there's one thing we have to remember, is that we were dealing with this fraction originally for a reason. And when we look at this denominator, x squared minus 4, we still have to think about values that are not allowed. Denominator cannot equal 0. True, we're thinking vertical asymptote in this case, but we'll go back to the graph to make the final connections here. X plus 2, x minus 2, we know other factors. So we solve this equation, get x equals negative 2 or x equals positive 2. Now usually we're thinking about these values as vertical asymptotes, but only one of them is working like the vertical asymptote, the one that is still there in our simplified fraction. So we will definitely see a vertical asymptote at x equals 2, but we're not going to see the vertical asymptote at negative 2. But it still is a value that is not allowed. So we actually are just going to put a little hole in the graph. The graph, let's go back to them. So we're looking at the graph of 3x squared plus 8x plus 4 over x squared minus 4. Algebraically, we showed we could simplify. It does show us that we'll have a vertical asymptote here at x equals positive 2. I can draw a straight line. But what about that other x value not allowed at x equals negative 2? We don't see the vertical asymptote because that factor was divided out when we simplified the fraction. What we need to do instead is put a hole in the graph right here. So our graphing software didn't show us that hole in the graph. We know it is there. The function could be simplified, and that is basically what our graph looks like, is the simplified fraction. But still, we have to look at our original function to figure out what x values are not allowed. And if one of those x values came from a factor that was canceled when we simplified, then it becomes a hole in the graph. This idea is also one that we're going to look at in our last example right now. This last example, x squared minus 7x plus 12 over x minus 4, was the graph that just appeared to be a straight line. No matter how far we zoomed out, this one was somehow just a graph of a linear equation. Let's take our function, x squared minus 7x plus 12 over x minus 4. We can simplify. I picked one not too painful this time. X minus 3, x minus 4 is our factored numerator over x minus 4. And the x minus 4's divide out. We're left with just x minus 3. So no vertical asymptote. Even though we have a value that is not allowed, x cannot equal 4. It's not showing up as a vertical asymptote this time. And we mentioned briefly way back at the beginning when we first started talking about vertical asymptotes that values that make the denominator 0 are almost always becoming vertical asymptotes. The only times that they're not are examples like these, where those factors eventually are canceled out or divided out when we simplify the fraction. So no vertical asymptote, but we do need to make an adjustment about x cannot equal 4. Even though it simplifies here and you're telling me, well, 4 minus 3 equals 1, and even at 4 on the graph, we see the function is at positive 1, I'm telling you that you have to look at the original function, especially about these values that will make the denominator equal 0. And when they cancel out, it's not a vertical asymptote. Instead, it is a hole in the graph. So that is the graph that I would like to see for this rational function. To sum up, let's look at one last graph. We have seen some interesting and pretty cool, to me, looking graphs, but do we really need these? And the answer, of course, is yes. Here's an example. Okay, another nice looking graph, a brand new example. It's 5x over x squared plus 1. So what I'll do to this graph, what I want to see is I'm focusing here in quadrant 1. It's got a little bit of a spike, a quick increase, and then it peaks and it starts to level off gradually. So to this function, I'm going to do some things. First of all, I'm going to make it 5x over x squared plus 1, and then add into it 98.6. And we should remember about transformations, that if I just take a number and add it to this function, it's shifting the entire graph up vertically. So I'm going to do that. So we've shifted this graph up by 98.6 units. Let's find it. It's going to have the same shape and everything, just shifted up. Here it is. Instead of crossing at the origin, it's crossing at 98.6. There's our y-intercept. And the next thing I'll do is make up a little story about what this graph and this function represents. Last year, I was bitten by a poisonous... No, that's not... I ate something poisonous. Bad mozzarella sticks. Now our x values represent time, so 1 hour, 2 hours, 3 hours, 4 hours, and so on. And this function represents my temperature. Right at x equals 0 is when I first ate the mozzarella stick. So I'm not even looking at this part of the graph. I'm looking only at what we've got in quadrant 1. And after about 20 minutes, I started to feel it. I had a temperature of 100. And after 1 hour, I was up to a temperature of 101. I was not doing so well. But I didn't eat that much, so I was starting to, at that point, kind of get on top of it, and body started doing its work, and the temperature slowly started coming down. And it gradually went back to normal 98.6, took about 24 hours. So what I want to point out to you with this example is that definitely we can get some pretty interesting looking graphs, but graphs that do interesting things, that they're not so symmetric, that maybe they increase quickly and then decrease slowly, those apply to many things in life. So they're very useful models. So rational functions are very important functions for us to work with. We definitely want to utilize software and calculators for making graphs, but definitely algebraically there is a lot to be known about those asymptotes. The vertical asymptotes are the x values that would make the denominator equal 0 and therefore our function undefined. Horizontal asymptotes, where our function will level off, thinking about x values that get very large. And then oblique asymptotes, for those cases where the numerator has a degree that is higher just by 1. We can divide evenly to find an equation of a line that is going to be the oblique or diagonal asymptote.